6-2, day 1 is where we're at, okay? Remember in 6.1, we really just kind of focused on angles, okay? How we measure them, degrees or radians, their definition, complements, supplements, coterminals, all that stuff. The focus in 6.2 is going to switch to what we call the trig functions, okay? They're listed there in the box. You can see them. We've got 6 of them. They come from looking at an angle. Right now we're defining it as an acute angle because we're working within the context of a right triangle, okay? Later on in chapter 6, that'll change, okay? So this angle theta down here that's marked, okay, given the fact that it's in a right triangle, as this angle is marked as 90 degrees, I know it has to be acute, right? The two non-right angles in a right triangle, mathematically, both have to be less than 90, okay? So it kind of just leave that thought for the moment, like, okay, like, what if we had a 120-degree angle? Does that have a sine or a cosine value? The answer is yes, it does, okay, but just leave that. Okay, that's later on in chapter 6, that's a question we'll definitely address. Right now we're saying angles that are less than 90 degrees, and that's that. All right, so the 6 trig functions come from the ratios of side lengths that are formed in a right triangle, okay? I'll use the sine function as an example, all right? That angle that I've marked, theta, has a sine value. It comes from taking the length of, I'm putting on the same labels, but I'm just kind of making them bigger, okay? The side that is opposite divided by the hypotenuse. Hypotenuse is always your longest side. It's always opposite the 90-degree angle, okay? Again, I know these labels are there. I'm just making sure they're big and obvious and easy to read. Okay, there's adjacent, which basically means next to, okay? What these ratios are basically saying is each angle have unique, well, they have 6 trig values, okay? Every angle has a sine, cosine, tangent, cotangent, secant, and cosecant value that come from the definition of those ratios that you see. It doesn't matter how big the triangle is, okay? Let's just say, for example, theta over here was 40 degrees, okay? Doesn't matter how long the sides are. The ratios between all the sides, and if you look at the trig functions, you can see they're really about these ratios of side lengths. They're the same. You could draw an absolutely massive right triangle, but if that angle down in the bottom left corner is 40 degrees, all these trig functions are going to be the same ratios, okay? If you change the angle, you're going to change the trig values, okay? Now I'm going to add a little sketch for this, because if I'm asked to find an angle's trig values, right, off of it giving me one, I just draw a quick little picture. You can put the angle in the top right. That doesn't matter, okay? I notice my picture's not to scale. I don't even know what the angle is, okay? I could make the triangle to scale off the side lengths, but I won't. Okay, but it tells me its sine value, which is opposite over hypotenuse, is 4 over 5, okay? Now I've got this other side here. I'm trying to figure out what it is. Relative to theta, it's the adjacent side. We'll call it x. I use the Pythagorean theorem. to figure out my missing side length, because once I have it, getting all 6 trig functions, or essentially the other 5 because I was given one, is pretty easy to do. Subtract 16 and I get 9. Okay, here's one that works out really nice with the numbers, that the adjacent side is 3. Okay? So now, once we have a diagram like this, off we go with the trig functions. Okay? Remember, this side's opposite, this side's hypotenuse, and you basically just apply the definition that fits that trig function. Like cosecant is hypotenuse over opposite. Cosine is adjacent over hypotenuse. I'm doing secant next because those cosine and secant are what are called reciprocal trig functions. Notice it's the number flipped, right? And then you look in the definition and you're like, oh, cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. It's just the ratio flipped. Notice the same thing between sine and cosecant, and the same thing happens with tangent and cotangent. Tangent is opposite over adjacent, cotangent adjacent over opposite. Okay? We're going to do another one, except I'm going to throw a little wrinkle at you on this one. I got to be a little more careful of space. My diagram, there's theta. All right, so it says secant is 6, right? This one can be a little bit tricky, but when it says that, I like to switch it to a ratio. And remember, you can always do that. If you just have a whole number for a trig function, just throw it over 1 so you see that, all right, because when I'm looking at secant, I'm thinking, all right, the top number in the ratio, that's your hypotenuse. And then the bottom number is your adjacent side. 6 and 1, and then we've got this side over here that's missing. Same deal as before. Use the Pythagorean theorem to figure out what is our missing side. Solving for x with the exact same set of steps that I did before, but what I want you to notice is the numbers don't always work out like they did in the first one, and I get a number like the square root of 35. Now, when you're solving for a missing side in a right triangle, this is typically like more often the case that you're going to see this happen, okay? That you don't get a nice whole number like 3. It can happen, it doesn't happen that much. Okay, usually you're left that one of the sides has got a square root in it, okay? That doesn't change anything about the definitions of the trig functions. It'll change a little bit about how I write my answer. I'll go with the reciprocal of secant, that's cosine, 1/6. Here's sine, opposite over hypotenuse. This one doesn't really change anything. It's the square root of 35 over 6. Here's where you'll notice a little bit of a difference. Right? I go to cosecant, which just according to the ratio says 6 over square root 35. I do need to make sure to rationalize my denominator. Okay? That's the new piece I was talking about, that if you have a side length that's expressed as a square root, like this one. By the way, I should have mentioned that I should also check to see if I could reduce the number under the radical. Like, could I make 35 smaller? You couldn't, okay? You could do it, but just a reminder to check that you would look for factors that are perfect squares. Like 4, 9, 16, that type of thing. 35 didn't have them. But if you get that number that's underneath the radical down on the bottom, make sure to rationalize your denominator. That's all. Really the only difference, and honestly, it's the biggest thing I wanted you to see in the second example. Tangent is the square root of 35 over 1. Cotangent is 1 over square root 35. Okay, just a reminder that that's coming from adjacent. All right, I could go label my sides here. The side length that was 1 was adjacent. Square root 35 was the opposite side. 6 was the hypotenuse. Now, I set up my diagram the same way because I didn't want it to be confusing. I could have picked to say theta was the angle in the upper right. Then the labels on the sides would switch. Because remember, when you label the side, it's not like, these side lengths are labeled opposite, adjacent, and hypotenuse no matter what, right? It depends on the perspective that you're looking at the triangle. I'm doing it from this angle. If I had switched and said I'm working with this angle, hypotenuse would stay the same, but opposite and adjacent would switch. Okay, so you got to know when you're doing the opposite adjacent thing, you got to start with the angle. What's kind of the angle that I'm looking at this triangle from? All right, this would get rationalized to the square root of 35 over 35. All right, you're going to see certain angle measurements in trigonometry just come up a lot, okay? Typically speaking, any multiples, we're just looking at kind of the basic sine and cosine values, but multiples of 30 degrees and 45 degrees, or if you want to talk radians, okay? Which is always a good reminder, pi over 6 and pi over 4. They come up a lot, okay, to the point where it's worth having a page in our notes where it's like, let's just go through and hit all the trig functions. Well, not all of them, actually, just sine, cosine, and tangent, okay, which is kind of a bigger picture thing if you compare it to what I did on the last slide. You'll see we look at trig functions more often from the perspective of sine, cosine, and tangent, with the understanding that if we want the other three, all we have to do is just flip the three numbers that we have, okay? You found your sine value, okay, good. If you wanted cosecant, just flip your sine value. If you want secant, just flip your cosine value. If you want cotangent, just flip your tangent value, okay? Now, before I look at this, I do need to make a reference right here as to what that is. Pythagorean theorem, here we go again. There's basically no limit in trigonometry as to how often the Pythagorean theorem can just kind of show up. Okay. Sometimes you see these two triangles referred to as special right triangles. The one on the left is called a 45-45-90. That refers to the measurements of the three angles. The one on the right is a 30-60-90. Okay. All right, we'll start kind of on the top row and work our way over. Sine of 30 degrees, right? If I'm doing 30 or 60, I'm over on the diagram on the right. Opposite over hypotenuse would be half, or 1/2. if you're feeling pretty confident with writing an angle's trig function, not a bad time at all to pause, right? You've got, 9 more trig functions to write in. Feel free to go for it and see if you can fill it all in and then make the adjustments if you get any wrong, okay? If you don't feel confident doing that, just keep cruising. Keep cruising and go with me. All right, cosine adjacent over hypotenuse. Tangent opposite over adjacent, square root 3 over 3. Okay. Pi over 4, okay, or 45 degrees, we're moving over to the diagram on the left. I'm kind of bouncing back and forth between the two. I'm working on the first line is the 30, 60, 90, then I bump over, and then we'll bump back for 60 degrees. All right, sine of 45 is 1 over the square root of 2, which would be better expressed as square root 2 over 2. You don't see this happen very often. Cosine value is the same thing. Right? 45 degrees is a really unique angle that its sine and cosine value are the same number. Tangent, opposite over adjacent, right? And I know the 45, 45, 90 triangle just had the 3 side lengths already filled in. You know, if you really wanted to convince yourself, I mean, plug them into the Pythagorean theorem to verify that it works, right? Those are, you know, if your 2 shorter legs, the opposite and the adjacent side are 1, the hypotenuse comes out to be the square root of 2. I kind of skipped over that, but you can verify it. It's true. All right, back over on the 60-degree angle now. Square root 3 over 2. Cosine of 60 is a half. Tangent is square root 3 over 1, which is square root 3. All right, on the next slide, I'm going to start to show you what are called identities. We'll see a bunch of them throughout the semester, okay? Identities are like equations that involve trig functions that have just kind of some basic properties that we know to be true, okay? One of them is going to kind of build off of these because you're seeing basically this thing right here. Let me show you this. Sine of 60, cosine 30. Sine of 30, cosine 60. Okay, I want you to see specifically here the pattern that if you had 2 angles that added up to 90 degrees, right, like 60 and 30, and you swap the trig function, sine to cosine, you end up with the same trig value, okay? In other words, we're seeing here that the sine of 60 degrees is the same thing as the cosine of 30. Likewise, the sine of 30 is the same value as the cosine of 60. Okay, on this next slide, we're going to generalize that because it's also true for other trig functions as well. Okay? Don't get confused by the notation, right? This 90 minus theta, like theta is the angle that you have. In the example that I just showed you, let's say that theta was 30. Okay, if that's the case, 90 minus theta would have to be 60, right? So when you're seeing this little pattern of theta and 90 minus theta, it's an angle, and then the angle, I mean, if we want to go back to our vocabulary, an angle and its complement, okay, is what these co-function identities are all about, okay? Now, I showed you on that previous slide a little example with sine and cosine. This whole co-function thing is true for tangent and cotangent and secant and cosecant, okay? Now, in this diagram, I'm going to show you a little bit about why this happens. Now, because this question, it gives us a secant value. I can't just directly apply the identity, because that's a lot of times what identities can be used for, is you could apply them to a geometry situation involving some trig functions, and you can get new information quickly and easily without drawing any diagrams. This one doesn't quite work out great because it gives me the secant value of theta, and the identity I have for that is if this was cosecant, it would be the exact same number, okay? But it's not, so I do need to make a diagram. But and within this diagram, this question will kind of show you as to why these co-function identities work out, okay? Why they're valid. By the way, in a right triangle, if I wanted to call this other side 90 minus theta, I could, okay? Those two non-right angles not only have to be less than 90, they have to add up to exactly 90, okay? So the secant value of theta is square root 13 over 3. That's hypotenuse over adjacent, okay? So there we go, and look at that, yet again. Good old Pythagoras and his lovely theorem shows up. I'm writing these out because these examples are in your notes. If you get to the point in your homework assignments where, you know, on like a test, I would expect you to write it out because I need to see all your work. But in a homework assignment, if you need to do a quick Pythagorean theorem, I understand when you're doing like multiple repetitive practice problems, this work I'm writing out might happen in your head, okay? Might happen in your head, and that's okay. Take away 9 and get that x squared is 4. Take the square root. There we go. Missing side length was 2. All right, this whole problem, it wants me to get the secant value of 90 minus theta. Okay, now I'm kind of switching perspectives, right? I'm not looking at the triangle from here. Rather, I'm looking at it from here, okay? Hypotenuse is still the square root of 13, but now the side adjacent is no longer 3. It's now 2, okay? But another thing I want you to see, right, if I go back to this co-function identity, okay, I switch over to this other angle on the top right, 90 minus theta. Cosecant would be hypotenuse over opposite. Okay, well, if I'm looking from 90 minus theta, the opposite side is 3. If I were looking at the triangle from theta, the adjacent side is 3. Okay, which is why it would end up being the same value. Okay, which again, for the example we did, I wanted you to see that laid out in the diagram. That didn't really address our question because we couldn't just go to an identity because we had secant theta and secant of 90 minus theta, and you look through your list of identities, there's not one on there that relates secant theta to secant 90 minus theta, okay? Again, if it was cosecant of 90 minus theta, we're in luck, but it wasn't, okay? Well, for day 1, we're going to call it quits there, okay? Good place to stop. Day 2, more to come on identities.